to systems with eigenvalues of multiplicity 2, and specifically with eigenspace dimension 1. General idea here. So again, let's consider the homogeneous system. Y prime equals AY, where A is an n by n constant matrix. Let's suppose that A has repeated real eigenvalue. Lambda 1 equaling lambda 2. Note it actually could have higher multiplicity for what we're doing here. With eigenspace dimension 1. Spanned by eigenvector psi1. Then we know that y1 equaling psi1 times e to the lambda 1t is a solution. If we follow the same technique used for ODEs with repeated root of the characteristic polynomial, so if we follow the same pattern as used for ODEs with repeated root in the characteristic polynomial, then what we would try is we would try just multiplying by t. And then we should try multiplying y1 by t. So let's go ahead and try y equals psi1 t e to the lambda 1t. So if we plug this into, plugging into the system, y prime equals ay, we get on the left-hand side, derivative of y, we would have psi1 times e to the lambda 1t from our first part of the product rule. And then we would have plus lambda 1 times psi1 times t e to the lambda 1t. On the right-hand side, we would have a times psi1 times t e to the lambda 1t. Now, psi1 is an eigenvector corresponding to eigenvalue lambda 1. And so we get the A times psi 1 is just lambda 1 times psi 1. So this becomes psi 1 times e to the lambda 1t plus lambda 1 psi 1 t e to the lambda 1t equals lambda 1 times psi 1 t e to the lambda 1t. And this will wind up giving us that psi 1 e to the lambda 1t is equal to 0. But this is not true. Psi 1 is an eigenvector. So this is a contradiction. Since psi 1 is not the zero vector. It's an eigenvector, right? So what this means then is that t times y1 does not work. So let's now do a slight modification. So instead, let's now try y equals, we will do psi 1 times t times e to the lambda 1t. But now we are going to add on an additional vector, a to 1 times e to the lambda 1t. So we're trying to add in something that can kind of balance out that psi 1 e to the lambda 1t extra term. So what we get then, if we plug this into, plugging into y prime equals ay, we get on the left-hand side, we would have, again, psi 1 e to the lambda 1t plus lambda 1 times psi 1 times t e to the lambda 1t plus lambda 1 times a to 1 e to the lambda 1t. And on the right-hand side, we just have a times psi 1 t e to the lambda 1t plus a to 1 e to the lambda 1t. Again, our right-hand side, that a times psi 1 is just lambda 1 times psi 1. So a times psi 1 is just lambda 1 times psi 1. And so we get, psi 1 e to the lambda 1t plus lambda 1 times psi 1 t e to the lambda 1t plus lambda 1 times eta e to the lambda 1t is equal to lambda 1 times psi 1 t e to the lambda 1t plus a times eta 1 e to the lambda 1t. Then our lambda 1 psi 1 t e to the lambda 1t's just cancel each other out. And if we rearrange this, rearranging this, we get A minus lambda 1 times the identity matrix, all times eta 1 times e to the lambda 1t should be equal to, I need to update my screen. So you have A minus lambda 1 times the identity, all multiplying eta 1 e to the lambda 1t should be equal to psi 1 e to the lambda 1t. And so we have A minus lambda 1 times the identity, all times eta 1 should be equal to psi 1. Now we already know A minus lambda 1 in is not invertible, so this has infinitely many solutions. Well, it should hopefully have infinitely many solutions if it has a solution. And so what we get is we will pick y2 to be we have our psi 1 times t plus eta 1, all multiplying e to the lambda 1t, where A minus lambda 1 times the identity, multiplying eta 1 is psi 1. And it does turn out that y1 and y2 form a fundamental, well, then y1 and y2 are linearly independent solutions. So our job now is to put this into practice. Let's go ahead and solve the example. Let's find the general solution to y prime equals the 2 by 2 matrix, 1, 4, negative 1, 5. So 1, 4 is our first row, negative 1, 5 is our second row, multiplying y. So the first thing we need to do is find the eigenvalues. So we have a determinant of 1 minus lambda, 4, negative 1, 5 minus lambda, setting this equal to 0. We're looking at 1 minus lambda times 5 minus lambda minus negative 4 is equal to 0. This is lambda squared. We would have minus 5 lambda minus 1 lambda becomes minus 6 lambda. Then we'd have plus 5 plus 4 is plus 9. And so we are looking at lambda minus 3 quantity squared is equal to 0. And we have lambda 1 is equal to lambda 2 is equal to 3. Our next step is to find the eigenvector or vectors. So for lambda 1 equaling lambda 2 equaling 3, we are looking at 1 minus 3, 4, negative 1, and then 5 minus 3, all times psi is equal to the 0 vector. So we are looking at the augmented matrix, negative 2, 4, negative 1, 2. with then augmentation, just the 0 vector. So if we row reduce, if we just do row 1 divided by -2, we would be looking at 1, -2, 0 for that first row. And then if we do row 1 divided by -2 plus row 2, we would have 0 for our first position, because that would be 1 plus -1. For our second position, we would have -2 plus 2, which is again 0 and 0. So we have one free variable in this case, but that's all. So we get the xi1 should be equal to 2 times xi2. So we can go ahead and pick our xi2 to be 1. That means our xi1 has to be 2. Since we only have one free variable, we only have an eigenspace of dimension 1. Right? So again, since we only have one free variable, we have our eigenspace has dimension 1. And so we are just getting a single eigenvector. We will pick the eigenvector to be the vector xi1. Has 2 in the first position and then 1. So since we only have one eigenvector, our next step is to now find eta. So since we had λ1 equals λ2, but only one linearly independent eigenvector, our next step is to find eta 1. And so we will be solving A minus λ1 times the identity times eta 1 as equal to xi1. Now, A minus λ1 times the identity is precisely the matrix we were already working with. I'm just going to rewrite it just to have it. So we have 1 minus 3, and then 4, and then we had -1 and 5 minus 3. We're multiplying eta 1, and we are looking to land on our xi1, which we picked to be 2, 1. Let's update my screen one more time. So this becomes the augmented matrix. We have -2, 4, and -1, 2 for the main component of our matrix. And then with augmentation, 2, 1. So again, if we row reduce, we can do row 2 divided by -2, sorry, row 1 divided by -2. And that gets us to 1, -2, and -1 for the full first row. And then if we do row 1 divided by -2 plus row 2. We would have 1 plus -1 is 0. We would have 2 plus -2 is 0, and 1 plus -1 is 0, or -1 plus 1 is 0. So again, we have a free variable. And we also know that eta 1 minus 2 times eta 2 is equal to -1. At this point, because we have a non-zero number on the right, you are welcome to pick either eta 1 or eta 2 to be equal to 0. So let's go ahead and pick eta 2 equal to 0. Then that means that our eta 1 would just be -1. And so what we get then is our vector eta 1 is simply -1, 0. Note there are many different vectors we could have chosen for this. They do not have to be scalar multiples of each other, since we have a non-zero right-hand side. So this is a case where you will start getting solutions that look much different students will get very different looking solutions. But at this point, all we need to do is form our solutions. So form our fundamental set of solutions. So we have y1 is psi1 e to the lambda 1t. We have y2 is psi1 times t plus eta 1 all times e to the lambda 1t. So plugging in what we had, our psi1 was the vector 2, 1. That's multiplying e to the 3t. For y2, we have the vector 2, 1 multiplying t plus the vector -1, 0. And then that whole thing is multiplying e to the 3t. We often see y2 written sort of combining two vectors. So performing the vector addition, we would have 2t minus 1 for the first position, and then t for the second position, all multiplying e to the 3t. So our fundamental set we have found, and then finally the general solution. So we have y is equal to c1 times the vector 2, 1 times e to the 3t plus c2 times the vector 2t minus 1 and then t all times e to the 3t. So this is a 2 by 2 case. In the next video, we'll go ahead, in the next couple of videos, we'll look at both the 3 by 3 case, where we have just a multiplicity 2, an eigenspace of dimension 1, and we'll also look at the trajectories that we see when we have solutions of this form.